Okay, so we just looked at hydrogen bonding and saw that positives like negatives. So this is a little bit more with the positive negative thing, not hydrogen bond. So remember, hydrogens like NOF, N-O and F, hydrogen bonds with an H. So now we're looking at London dispersion forces, which is the force between non-polar molecules. Hydrogen bonds are polar. These are non-polar. So think of like carbon dioxide. It is a non-polar molecule overall because it is linear. So when you're looking at these, it's important to look at the instantaneous electron arrangements. This means where the electrons kind of hang out, right? At an instant, the position of an electron can force a temporary dipole moment. It just means just because where the electrons kind of float and move around the nucleus, it could cause one side to be more negative than the other side. That's all it's saying. So the temporary dipole moment can induce its neighbor to experience a dipole moment, causing an attraction. So it could momentarily be attracted to something else, but then be repulsed away and then attracted again. Just depends on where that electron is. This force is only significant when the molecules are very close to each other. It won't happen if it's like this far away. It's not going to happen. It's not going to be like, ooh. But if they're like this, they could be, a little bit and then a little bit away. It doesn't have to be, it's got to be kind of close. So this is like a van der Waals type thing going on. The van der Waals interaction as opposed to the London dispersion force. So the force causes a van der Waals. Okay? Where at some point in time, all the electrons are over here, making it more negative. Well, same with this one. So the positives, they attract. And notice they're not far away. It's not like they're coming from like way over here. They're like this far and they're like, ooh, okay, and then away. So the amount of polarizability, I still can't say that word, and the strength of the dispersion forces increase with the size of the molecules. The bigger they are, like the farther away they could be, the farther that force could pull them together, causing the van der Waals attraction. Then the force pushes them away, okay? As a result, boiling point increases with molecular weight. So looking at this, as they get bigger, boiling point gets bigger. As they get smaller, boiling point decreases. Same with neon through xenon. All right, London dispersion forces is also why we can get dry ice or liquid nitrogen. The only reason we can do this is because of these the London dispersion forces or the van der Waals. Otherwise, it wouldn't happen. It'd be impossible to exist if we didn't have this force, this instantaneous dipole. So looking at this, you have ionic, metallic, then covalent. Ionic is taking. That's the strongest. It's hard to break. Metallic is flowy, so it flows through all of these. So it's a little bit less not as strong as ionic. And then you got covalent where they're sharing. So yeah, you can break those apart. And then comes the forces, the hydrogen bonds. Those are less than the ionic, less than the covalent, because you can break them up, but they're still kind of hard to break. Out of all the forces, hydrogen bonds are the hardest to break. Then you have the dipole. Then you come to the London dispersion attraction with the van der Waals. All right, ion dipole attraction. This is the last part. This is important between an ion and a partially charged polar compound. So we're looking at ionics with covalence. So what's going on? Well, in the ionic, a polar covalent positive attracts to the negative in the ionic. Whereas in the ionic positive is attracted to the polar covalent negative. Where do we see this? Well, this is very important in aqueous solutions. So say I'm throwing salt, an ionic, into water, a covalent. It doesn't really break it up. It makes it, it pulls apart the ions, but the ions are still considered an ionic bond, right? So the cation of the ionic is pulled away by the negative oxygen of the covalent, polar covalent, whereas the negative anion of the ionic is attracted to the hydrogens in that hydrogen bond of the water. So it pulls it. It doesn't break it. It pulls it. Where when you evaporate, when you get rid of those covalent bonds, that covalent water, you're left back with the salt. Because of its polarity, water dissolves most polar ionic substances, making it a universal solvent. Here's the thing that I told in class that I'm saying again. When it comes to solubility, like dissolves like, polar with polar, nonpolar with nonpolar. Keep that in mind for the next unit after stoic. So we're looking at this. This is just showing that the negatives like the positives, and that's what's going on right here. All right, just a summary, quick summary. Let's look at this. Interacting molecules or ions. Is an ion involved? Yes, I have an ion. Is there polar molecules involved? And ions involved? Are polar molecules, polar covalent, and ions? Yes. We got ion dipole forces, like potassium bromide, aqueous solution, potassium bromide, and water. No, I don't have any ions. No ionic bonds involved at all. All right. Are polar molecules involved? Yes. All right. Are hydrogens involved? Is it a hydrogen bond? NOF. Is NOF involved with hydrogen? Yes, it's a hydrogen bond. No, they are not involved. No hydrogen, no NOF. Or NOF's involved, but no hydrogen. It's a dipole-dipole. Like hydrogen sulfide, CH3Cl, those type things. Dipole-dipole. Polar molecules involved? No, no polar molecules. It is non-polar. You got one, dispersion. All right, so make sure you finish up that travel log 5.4. Do the study guides on intermolecular forces. We have a quiz coming up. Besides that, type of bonds involved. Pure covalent, there is 0. The more you get, the more polar covalent with low electronegativity. The higher the electronegativity, the more ionic you get. All right, if you have any questions, please let me know. Besides that, I hope you guys have a great day.